Okay, I've been making some progress on getting the shift register to actually turn off and not draw any power. And it was a little trickier to verify that it wasn't drawing any power than I was expecting. Um, but I'll try to explain it, what all I did real quickly and the problems that I had to overcome. So let's see, where do I start? Okay, so let's go over the power rails here for the kitchen timer. There's this always on bus here, so positive and negative here. These are always on. They're hooked up directly to this up converter that's plugged into the batteries. And then you can see I've got a bridge here to connect the positive over to this side, then it goes over here with this line and then goes back. And then the negative is actually broken up with the NPN transistor. And but from here, this bus is the negative is connected, and it goes over here, and it goes to this negative over here, and then there's a bridge here, negative. So what this does is it allows me to power up all of these buses, all three, via this transistor. If I turn this transistor on and current flows, it'll allow current to flow through them. But when I turn it off, all these buses will be sitting at, I guess they're high. I guess they're like 5 volts. They're sitting at 5 volts, but they're not grounded because this transistor is breaking the connection and it won't let current flow. So, in order to get the shift register to not act weird and have that power draw, that current flow that it was having, what I had to do was on a couple of the lines, or all the lines that are going to it from the microcontroller, I had to set them to be high. I had to make them plus 5 volts. And so they're at 5 volts, and the buses are at 5 volts, sitting at 5 volts, and nothing is grounded. There's no ground anywhere, and then current won't flow. So that was good. And so in the code, it was not too bad. The master out, slave in, and the clock pins, I just set them to be high. And I also had to turn off the SPI communication. I had to do that too. So that was really easy in the code, and it acted just like it is right now. If I turn it on in a few seconds, here's the milliamp draw when it's on, and then it turns itself off. But then, hey, it's drawing milliamps, so 14 milliamps. Well, that's because of the LED that was built into the Arduino development board. It's also on pin 13, which happens to be the clock pin for the SPI communication bus, and you can't change that because I'm using the hardware SPI. Maybe I should have used the software SPI, but I'm doing the hardware one because it's really fast. So because of that, I can't change the pin. The LED was there. The LEDs draw power. I had to do a little bit extra work. So I got one of my microcontrollers that I'm going to put in the kitchen timer, the actual microcontroller, and I put it onto a breadboard, and then I got online and I figured out all the parts you gotta stick in to make it act like the development board, and including for this demo, I put the pin 13 LED in here. And one thing that made it a lot easier to hook everything up was I found one of these PDFs that somebody made that's got the pin mappings printed out so that all the pin numbers that are on the development board are available or labeled on the microcontroller real easy. I just taped that on. So I was able to plug up the circuitry pretty quickly to it after I did that. And now if I go and if I unplug the LED, so this cost a lot of work, but I can do it now. I can verify that sure enough it's not drawing any more microamps than it was before in its powered off state. So it stays under the 20 microamps, and it's actually off. So there you go. That's all you gotta do. You just gotta build a breadboard version so you can unplug the LED to verify it.